Hi everybody, I hope this video finds you well. In today's video, we're going to be working through practice number 11, which focuses on the chi-squared and Anova procedures. As usual, before watching this solutions video, I recommend making sure that you've already watched all the videos on the chi-squared procedures and the Anova procedures, and you've tried the 3 questions on this practice sheet. If you've already done that, well, then let's go ahead and get started with these solutions. So let's take a look at question 1. For question 1, we're going to suppose that a large company wants to study if there's a relationship between the department an employee works in and their job satisfaction. We get this note that we can assume that the company has around 8,000 employees. To study this, the company randomly selects 250 of their employees, records which department they work in, and asks them if they are very satisfied, satisfied, or not satisfied with their job. And they get the following data, which is presented to us right here. We've got 2 things that we want to do here. First, we're going to try to carry out a hypothesis test at alpha equals 0.05 to test the claim that there is a relationship between the department an employee works in and their job satisfaction at the company. And then in part B, we're going to build a 95% confidence interval for the percentage of research and development employees, so one specific department of employees, research and development, who are very satisfied with their job. Okay, so let's do a couple things before we get started with this. First of all, in part A, we have to carry out a hypothesis test. So that means we need to know which hypothesis test are we supposed to run here. At this point in our course, we have a bunch of different hypothesis tests. You guys have learned how to do 1 sample mean procedures, 2 sample mean procedures, matched pairs, 1 sample proportion procedures, 2 sample proportion procedures, the chi-squared test for independence and homogeneity, the chi-squared test for goodness of fit, and Anova. So that's a ton of different procedures. Which one are we supposed to run here? Well, there's a couple major things. First of all, the data here that is given to us in a 2-way table. By seeing this in a 2-way table, we know that means that the variables that are being studied here, job satisfaction and department that the employee works in, are categorical in nature. We also know that the hypothesis test that corresponds to data that comes in a 2-way table is a chi-squared test for independence and homogeneity. So this should be one of the easiest tests to identify. As soon as we see this 2-way table, we know we're going to be using a chi-squared test for independence and homogeneity. So let's go ahead and get started on that on the next page. So here's our data. We know that whenever we see a 2-way table, no matter what we're going to be doing with it, we want to add the row and column totals as well as the table total. So let's go ahead and get started with that. We're going to annotate this. I'll do the row totals first. So 63 plus 28 plus 21. Looks like we should get a total of 112 there. Then 60 plus 17 plus 15. Looks like we should get a total of 92. And then 28 plus 9 plus 9, we should get a total of 46. Then for column totals, 63 plus 60 plus 28, looks like we should get 151. 28 plus 17 plus 9, 54. And then 21 plus 15 plus 9, looks like we should get 45. Then we can do the table total, either summing up the row totals or summing up the column totals. Either way, we're going to get the same thing. So I'll add up these. So 112 plus 92 plus 46 gives us a table total of 250. Now, this 250 should not come as a surprise to us because remember the table total always corresponds to the sample size. And if we look back at the question, it did mention that we randomly selected 250 of their employees. So of course, the table total was going to come out as 250. All right, now that we have that, we can actually start into our hypothesis test. So like we said, the fact that we have this 2-way table is telling us that we're going to be using a chi-squared independence and homogeneity. Now, there are some other indicators. The 2-way table is probably the easiest way to spot that we're supposed to run a chi-squared independence and homogeneity. But again, we can also look at what we're actually sort of testing as our claim. So if we go back to the original problem, let's just tab back over there. There we go. So if we go back and look at the original claim, notice that the claim here says that there is a relationship between the department an employee works in and their job satisfaction. So remember, the type of test that is used to study if there's a relationship between categorical variables is a chi-squared independence and homogeneity. So again, you can realize that this is an independence and homogeneity test either by the way that the data is presented, a two-way table, or by the fact that there's this mention of, is there a relationship between these two variables? Okay, so let's go ahead and get started then. Every hypothesis test we have is a 5-step process, so we got to start with the hypotheses. All right, so let's go ahead. What does the HO and HA look like? Well, remember, independence and homogeneity is a little unique. We actually don't write out anything mathematical for the null and the alternate. Instead, we sort of describe what those would be. So remember, the baseline assumption is that the two variables should not be related. In other words, they have no connection to each other. So we would say the null hypothesis here is department and job satisfaction are not related. So that's our baseline assumption. And then our alternate is that department and job satisfaction are related. Now, it's always a little bit weird to people that the null is that the things are not related, but remember, that should make sense. The null hypothesis is your baseline assumption. So if you just have two random variables, your baseline assumption about them is they're probably not related. The burden of proof is on showing that they are related, which is why the alternate says the two variables are related. So this is always the setup for hypotheses for a chi-squared independence and homogeneity. All right, let's go ahead and get to the conditions. However, as we know, before we can actually get to the conditions, one of those conditions in a chi-squared independence and homogeneity is based around the expected counts. So we have a little intermediate step here, and we're going to build our expected counts table. Remember, this is not only important for the conditions, but it's also what's going to pretty much dictate how we calculate the test statistic. So how do we build the expected counts table? Well, we're going to recreate the table. So there's very satisfied, satisfied, not satisfied. And in terms of departments, we can just abbreviate marketing, research and development, and finance. So there we go. Okay, so there's our table. And we need to fill in these 9 values in here. How do we do that? Well, remember, for independence and homogeneity, what it is that you're going to take the row total times the column total divided by the table total. So let's see how to do that. So for this first one here, what we're going to do is we're going to take the row total, which is 112, times the column total, which is 151. So we'll take 112 times 151, and then divide by the table total, which is 250. On your calculator, you should get that that comes out to about 67.6. I do usually like to leave at least one decimal place here, if only just to distinguish between expected counts, which are again expected, so they could be possibly a decimal, whereas these up here are the observed counts. This is what really happened in our data, and of course these have to be whole numbers because each of these represent an amount of people or individuals. All right, what about this value here? Well, we'll still use 112, but we'll multiply by 54 and then divide by 250. So 112 times 54 divided by 250. Looks like we should get 24.2. And then finally, for this one here, we'll take 112 times 45 divided by 250, and we should get about 20.2. And of course, if you want to, you can check that these 67.6, 24.2, and 20.2 sum up to 112. Remember, we're not changing what the totals are. We're changing how these values might have been distributed if there really was no relationship whatsoever. All right, let's do the next row. So here we will be doing 92 times 151 divided by 220. So 92 times 151 divided by 250. Looks like we should get 55.6. Then for this guy here, we'll be taking 92 times 54 divided by 250. So 92 times 54 divided by 250. Looks like we should get 19.9. And then finally, right here, we'll be taking 92 times 45 divided by 250. So 92 times 45 divided by 250. Looks like we should get 16.6. Finally, for our last row, our row total now will be 46. So the first one will be 46 times 151 divided by 250. Looks like we should get 27.8. Next one should be 46 times 54 divided by 250. That should be 9.9. And then finally, 46 times 45 divided by 250. Looks like we should get 8.3. So there we go. There is our expected counts table. All we're doing is a row total times column total divided by table total for each one of these values. Okay, now that we have that expected counts table, we can go on and check our conditions. So let's go ahead and do that. So our first condition is that the data has to be random and representative. Let's go back and just check the text real quick. It does mention right here that we randomly selected the employees, so that is stated. So we're all good there. The second thing is we need to make sure that the sample size is less than 5% of the population size. So we know the sample size. Well, that's always something we know when we're performing any sort of hypothesis test. In this case, it is at 250. Do we know the population size? Well, that's up to the information that we're given. So let's go see. Was there any information provided about the entire population? Well, we had this note. You may assume that this company has around 8,000 employees. So that right there is our population size. So let's go ahead and check then. So we have n equals 250. Is that really less than 0.05, which is 5% of 8,000? So we can just check on our calculator. 0.05 times 8,000, that is 400. Is that a true statement? 250 less than 400? Yep, that is all good. So we're good with condition 2. Finally, for condition 3, this is the condition that basically changes for each hypothesis test. It's sort of unique to the given hypothesis test. For condition 3, for chi-squared ones, it's about this expected counts. So remember, this is that no more than 20% of the expected counts are less than 5. So let's think about that here. In this case, we built 1, 2, 3, 4, 5, 6, 7, 8, 9 expected counts. So we had 9 expected counts. Out of those 9 expected counts, how many were less than 5? Well, the lowest expected count we had was 8.3. That's still not less than 5. So we had 0 out of our 9 expected counts less than 5. 0 out of 9 is 0%, and that is certainly less than 20%. So we are all good there. Now, what would have happened had this guy, say, come in as like 4.2 or 4.3? Well, then we would have had 1 out of 9. And 1 out of 9 would be about 11%, and we'd still be good. What would happen if we had like 4.3 here and 4.2 there? Well, then we would have had 2 expected counts out of 9 less than 5. 2 out of 9 would be 22%, and then we would fail condition 3, and we would be unable to continue with the hypothesis test. So here we're all good because none of the expected counts were less than 5. All right, let's move on to our test statistic then. So we'll go over here for our test statistic. Remember, this is one of the more computationally intensive ones. So what type of test statistic are we calculating? Is it T or Z? Well, it's not. It's actually the chi-squared statistic. So remember that the way we calculate that, chi-squared, is the sum of each of the observed counts minus their corresponding expected count squared divided by the expected count. So we're going to sum this up for each pairing of an expected count versus an observed count. And that means we're going to have to do 9 calculations here. So I will just give ourselves a little bit more space, just so it's a little easier to distinguish here. So let's go ahead and actually start this calculation here. So if we go ahead, our first observed count, remember observed counts are what actually happened in our data. They're up here. So our first observed count was 63 versus an expected count of 67.6. So our first calculation is 63 minus 67.6 squared over 67.6. Then we're going to add to that. Our next observed count was 28 versus an expectation of 24.2. So 28 minus 24.2 squared over 24.2 plus our next observed was 21 versus an expectation of 20.2. So 21 minus 20.2 squared over 20.2 plus, now our next observed was 60 versus an expectation of 55.6. So 60 minus 55.6 squared over 55.6 plus 17 versus that expectation of 19.9. So 17 minus 19.9 squared over 19.9. And then 15 versus that 16.6. So 15 minus 16.6 squared over 16.6. And then finally, our last couple here, we had this observed 28 versus that expectation of 27.8. So 28 minus 27.8 squared over 27.8 plus this 9 versus that 9.9. So 9 minus 9.9 squared over 9.9 plus our very last one, 9 versus that 8.3. So 9 minus 8.3 squared over 8.3. Now again, when I write out these questions, I always write this out. You guys are not required to write all of that out. What you are required to write out is the result of each of these 9 things. So if you want to just type these directly into your calculator, that's fine. What I'm about to write next is what you guys need to make sure you get down whenever you write up one of these chi-squared procedures. So let's start calculating these. For this first one, we'll just type it in as it looks. So parentheses 63 minus 67.6, close the parentheses, square it, and then divide by 67.6. So my first one looks like it should be 0.31 plus, then same thing, parentheses 28 minus 24.2, close the parentheses, squared, and then divide by 24.2. Looks like you should get 0.60. Plus the next one, 21 minus 20.2, square that result, and then divide by 20.2. Looks like we get 0.03. Then plus, next one, 60 minus 55.6, close up the parentheses, square it, and divide by 55.6. So 0.35. Next one, 17 minus 19.9, squared, and then divide by 19.9, so 0.42, and then 15 minus 16.6, and square that, divide by 16.6, so 0.15, and then 28 minus 27.8, square that, and divide by 27.8, looks like we should get 0.001, then 9 minus 9.9 squared, divided by 9.9, 0.08. And then finally, 9 minus 8.3. We'll square that and divide by 8.3. Looks like it should be 0.06. So remember, when you guys are doing a chi-squared procedure, this is what the work that you need to show. If you're comfortable with this formula, you don't need to write all this out. You just need to get the results here. All right, now let's go ahead and actually sum these up. So what is our overall chi-squared? 0.31 plus 0.60 plus 0.03, and then plus 0.35 plus 0.42 plus 0.15 plus 0.001 plus 0.08 plus 0.06. Looks like we get a chi-squared that results in 2.001. So there we go. There's our chi-squared test statistic. All right, now that we have that, we are ready to go ahead and get the p-value. So I'm just going to continue this down here. Okay, so step 4, we had to get our p-value. This means we need to go use table D. Table D is the one that tells us all our information about the chi-squared statistic, so we want to use table D. We do have to have a degrees of freedom for this. Degrees of freedom for chi-squared is a bit different than degrees of freedom for like table C and the t statistic. This is based on how many categories we allow our categorical variable to have. So remember, it is the number of rows minus 1 times the number of columns minus 1. So if we go back up here, we can see that we had 1, 2, 3 rows and 3 columns. So if we go ahead and do that, this is going to be 3 minus 1 times 3 minus 1, which is basically just 2 times 2. So we get 80 degrees of freedom, which is 4. So we have our chi-squared of 2.001, and we have a degrees of freedom of 4 here. So let's go ahead and look that up. And we'll find that on table D, which should be at the end here. There we go. So we're looking 4 degrees of freedom, so we're in this row right here. And remember, our chi-squared was 2.001. Notice that the first chi-squared value is 5.39, so we don't even make it onto the table. We would be right here with our t equals 2.001. So what does that tell us? Well, the p-values are up here. Remember, the p-values get smaller as we go this way. So ours must be up here, which means our p-value is larger than 0.25, because if the p-values get smaller this way, they must get larger this way. So since we're over here, our p-value must be larger than the largest value there, 0.25. So our p-value is greater than 0.25. So let's go ahead and record that. So we just found that our p-value comes in greater than 0.25. All right, then we can make our conclusion here. So 5, our conclusion. So we take this p-value and we compare it, as always, against the alpha that was set in the problem, 0.05. Okay, how does this p-value compare against 0.05? Well, we don't know what the p-value is exactly, but we know it's larger than 0.25 or larger than 25%. Certainly then, when we compare it against 0.05 or 5%, we know that the p-value must be larger. Remember, for any hypothesis test, when the p-value comes in larger than alpha, that means we fail to reject HO, which means we failed to find evidence for our claim. So we had no significant evidence that, what was our claim? Well, you can go back to the actual problem, or you can go back to your alternate hypothesis. Remember, the problem tells you what the claim is, and the alternate hypothesis is also the claim. And remember, the claim here was that department and job satisfaction are related. So we'd say no significant evidence that department and job satisfaction are related. So we have no evidence for a relationship here. Okay, now a couple quick notes about what this means. Does this mean that the people at the company are happy? No, not necessarily. Does this mean that people at the company are unhappy? No, not at all, right? That doesn't mean that either. All that this means is that it doesn't seem to impact happiness if we switch from different departments. In other words, all of the departments seem to have about the same level of job satisfaction. That could mean that they're all super happy. That could mean that they're all super unhappy. That could mean that they're all mixed. We're just saying that each of the departments seems to have the same job satisfaction. In other words, there's no evidence that the department you work in impacts your job satisfaction. Okay, so that is our conclusion here. So this was an example of the chi-squared test for independence and homogeneity. Remember, again, the main tip-off to perform this test is that there's a two-way table, or that the claim is about the relationship between two categorical variables. All right, we're going to need one more sort of page here. So let's give ourselves one more page, and we'll take a look at part B. So I'm going to just grab the text of part B here so that we know what we're sort of working on. So let's just do that. Okay, so let's go ahead and paste that in. All right, so we're going to be building a confidence interval here, and also, you know what, we should probably, yeah, we can just go ahead and grab our data again as well, since we'll probably want that. Okay. Okay, so there's our data. All right, so in this one, we want to build a confidence interval. Now, again, you guys have learned a lot of confidence intervals, but less than the hypothesis test. Remember, for confidence intervals, we have a one sample mean, two sample mean, matched pairs, one sample proportion, and two sample proportion. Well, right in here, we can see that we're trying to build a 95% confidence interval for the percentage. As soon as you see that word percentage in there, you know you're either talking about one sample percentage, one sample proportion, or two sample proportion. And notice it's the percentage of a particular group, research and development employees. So that tells us that this is going to be a one sample proportion. What would it sound like if it was a two sample proportion? Well, then it would say the difference in percentage between two groups. But in this case, it's the percentage of a single group. So this is going to be a one sample proportion confidence interval. Now, we have a lot of sort of data here, so we have to be a little bit careful. Notice that it's just about the percentage of research and development employees. So that means we're going to be focusing our attention just on this here. Also, remember that when working with a confidence interval for proportions, we have to have it be binomial, meaning successes and failures. So in this case, we're looking at the employees who are very satisfied with their job. That means that people who said that they were very satisfied are going to be viewed as the successes, and everyone else, regardless of if they said satisfied or not satisfied, are going to be viewed as the failures. So we're going to be sort of grouping our information like that. All right, let's go ahead and go through this then. For a one sample proportion confidence interval, remember confidence intervals are two-step processes. We have conditions. Okay, conditions 1 and 2. Those are the ones that are about random and representative and the sample size being less than 5% of the population size. These we've already checked, so we're all good there. However, we do need to check condition 3. Why? Well, because condition 3 for the one sample proportion confidence interval is about the number of successes and the number of failures. We haven't checked that yet, so we need to do that. So in this case, we can see that the successes are 28, and 28 people said they were very satisfied, and that is greater than or equal to 10, so we're all good there. And for failures, well, we had 17 and 9. If we just add those together real quick on our calculator, 17 and 9 gives us 26. So we had 26 failures, and that is greater than or equal to 10. So we're all good there. All right, now we can go to our construction. So for the construction, this is where we're going to use our formula. Remember, our formula for a one sample proportion confidence interval is p hat. The sample proportion is our point estimate, plus or minus z star square root p hat 1 minus p hat over n. So to fill in this formula, we have a couple things that we need to know. We need to know what is p hat, we need to know what is n, and we need to know what is z star. So let's go ahead and fill in each of these. So we might be tempted to say like n is going to be 250, but again, remember, we're only focusing on the research and development. What was the total for them? Well, we can just check 28 plus 17 plus 9 meant that that was 54 there. So remember, this had a total of 54. So that's going to be the sample size that we're going to be using there. So that's going to be our 54. How do we calculate sample proportion? Well, remember, sample proportion is always the number of successes divided by the sample size. So that, in this case, is going to be 28, and then divided by that 54. And let's go ahead and just calculate that. 28 divided by 54. Looks like we should get about approximately 0.519. And then Z star, well, that's based on your confidence level and table C. So let's go ahead and do that. You might already have these sort of memorized for Z star, but let's just go ahead and check. So Z star and 95%. So we're just going to intersect the Z star and the 95%. So table C is right here. So degree Z star is at the bottom. We'll have to zoom out a little bit more. There we go. There's 95% there. There's Z star. We put those together, and it looks like we get 1.960. So we end up there, and we end up right there, 1.960. So that is our Z star. All right, so we'll record that right there, 1.960, 1.960. All right, let's go ahead and plug all that stuff in. So we have 0.519 plus or minus 1.960 square root 0.519, 1 minus 0.519, and then divided by that 54 there. So let's go ahead and calculate that margin of error first on our calculator. So 1.960 times the square root, parentheses 0.519, times parentheses 1 minus 0.519, divided by 54. And looks like we should get 0.519 plus or minus 0.133 as our margin of error. Then we can build our interval, do our subtraction first, 0.519 minus 0.133. and we would get 0.386 plus or minus, oh, sorry, not plus or minus, comma, and then 0.519 plus 0.133, and that would be 0.652. So let's write our interpretation. Remember, for interpreting confidence intervals, we always go ahead and start with the confidence level. So 95% confident that between 38.6% and 65.2% of, well, would we say employees? Not quite. We only focused on the research and development employees. So only these employees. So we'd say of research and development employees are very satisfied. So in other words, we're saying that we're 95% confident that somewhere between about 38.6% and 65.2% of the research and development employees are very satisfied. This doesn't necessarily apply to other types of employees, but this would be our interval for this one particular department. All right, so this first question gave us a chance to look at chi-squared independence and homogeneity, as well as a quick follow-up with something a little bit older, the one sample proportion confidence interval. Let's go ahead and take a look at question 2. So for question 2, we want to study if El Camino students have a different taste in movies than the general U.S. population. So we find that in a study from 2015 that the U.S. had the following distribution in terms of favorite movie genre. 25% liked action, 33% liked comedy, 22% liked drama, 20% liked other. So to study this, we randomly select 8 classes from the class schedule list and ask every student in these classes, what is your favorite genre of movie? So we end up talking to 200 El Camino students. We have this note that there are about 25,000 El Camino students overall, and we get the following results. 65 said of the 200 said action, 69 of the 200 said comedy, 27 said out of the 200 said drama, and 39 out of the 200 said other. So what we want to do is we're going to start with a hypothesis test in part A. We want to carry out a hypothesis test at alpha equals 0.05 to test the claim that El Camino students have a different movie preferences than the rest of the U.S. population. Make sure to confirm all necessary conditions and state our conclusion in the context problem. And then we'll do a little bit of follow-up stuff with looking at what a type 1 error would mean here and also what type of sampling was used. So let's start by thinking about what type of hypothesis test this is going to be. So there's a couple ways to think about that, right? One is to look at what sort of variable is being studied here. So we're looking at your favorite movie genre. That's a categorical variable. So once it's a categorical variable, that means that we might be doing a 1 sample proportion, 2 sample proportion, independence and homogeneity, or goodness of fit. However, we know it's not going to be independence and homogeneity. The data is not presented as a two-way table. There's no mention of the word relationship. We know it's not going to be 1 sample proportion or 2 sample proportion as well, because the categorical variable in question here is not binomial. You're given 4 choices. 1 sample proportion and 2 sample proportion, you can only be given 2 choices, binomial. So that makes this a chi-squared goodness of fit. Another key word, though, if you prefer like a keyword sort of approach to identifying hypothesis tests, is this right here. The fact that there's a mention of distribution, that is really what tips us off that this is chi-squared goodness of fit. The chi-squared goodness of fit test is specifically for analyzing the distribution of a categorical variable. All right, so now we know that this is going to be a chi-squared goodness of fit. So let's go ahead and take a look at how we run that sort of test. So let's start with the hypotheses. So we have a null and an alternate. Remember that the null here is different than how we did independence and homogeneity. The null for chi-squared goodness of fit is the actual distribution that we think the variable should have. In this case, that's going to be that study from 2015. It told us what we expected in the U.S. Until we've studied the El Camino population, we would think the El Camino population as a baseline assumption is similar to the U.S. So we will be using these as our null hypothesis. We'll probably write those as decimals. So we would say like P sub A for action is supposed to be 25%, so 0.25. P sub D for... P sub C, comedy was second. P sub C would be 0.33. P sub D would be 0.22, and P sub O for other would be 0.20. So that tells us that these percentages right here, this is what we were using as our null hypothesis. Okay, what is the alternate going to be? Well, remember that the alternate in chi-squared goodness of fit is always the same thing. Since this is a global hypothesis test, it has a preset alternate. The alternate is that at least one of these is different. So at least one of these proportions is different. Now, if you go back over some of the lecture videos, sometimes we use the phrasing is different, or sometimes we use the phrasing has changed. We sometimes use the has changed when it's a time-based sort of analysis, like this was the distribution back in the year 2000. Has it changed until now? This time we'd probably use the phrasing is different, because instead we're interested in our El Camino students different than the rest of the general U.S. population. So we're saying is different here. Just a minor wording thing. All right, so now we have our null and we have our alternate. So let's go ahead and get to the conditions, but just like the previous one, we have that intermediate step of the expected counts. So we need to do an expected counts table. So we need to rebuild this little table: action, comedy, drama, other. We have to say basically how many people did we expect to find in each one. So we have to sort of come up with action, comedy, drama, and other. How do we do that? Well, the formula for this expected counts table for chi-squared goodness of fit is going to be that the expected counts is n times p sub I. What is the n? Well, as always, that's the sample size. What was that in this case? It's going to be those 200 El Camino students. And what are those p sub i's? Well, it's each of the values of the null hypothesis. So for action, what we're going to be doing is we're going to be taking 200 times 0.25, and we should get that the expected count there is 50. This might seem a little complicated, but actually it's very straightforward. What we're really saying is if 25% of Americans say that they like action movies, and we have 200 El Camino students, then we would expect 50 out of those 200 to choose action movies, because that would be 25% of 200. Then again, the expected count is the same. If El Camino is exactly the same as the national distribution, this is what we would have expected. Of course, these values back up here are what we actually observed, and we're going to be comparing how different is what we observed versus what we expected here. All right, so for comedy, we do the same thing. We take 200, the sample size, times the p sub I, which would be 0.33, so 200 times 0.33, and we should get an expectation of 66. Then for drama, we'll take 200, again the sample size, times 0.22, because that was its proportion there, and we should get 44. And then finally for other, we take 200 times the proportion in the null hypothesis there, 0.20, and we should get 40. If you want real quick, you can check that 50 plus 66 plus 44 plus 40 does give you 200. Again, we're not trying to change the sample size. We're just saying how we expected that sample to be distributed. All right, now we can move on to step 2, the conditions. So first one is random and representative. It is mentioned right here that our random selection, we actually selected 8 classes and ended up with 200 students. That might tell you that something a little strange went on when we get to part C. We'll talk about exactly what type of sampling that was. But the main idea right now is that it does say you did this randomly, so we're all good with the first condition. So this was stated. Okay. For condition 2, we have to check that the sample size came in less than 5% of the population size. Again, we always are going to know the sample size. We've already used it several times. It was n equals 200. The question is, do we know anything about the population size? Well, if we go back up here, we can see that there's this note about there being 25,000 El Camino students overall, so we can actually check this directly. So is this really less than 0.05 of 25,000? Well, if we do a quick check, 0.05 times 25,000 on our calculator, that gives us 1250. So is that a true statement? 200 less than 1250? Definitely, so we're all good there. Finally, for condition 3, it's the same condition 3 as we did with independence and homogeneity. We want no more than 20% of expected counts to be less than 5. So how do we check that? Well, how many expected counts did we make? We made 1, 2, 3, 4 expected counts. Were any of them less than 5? Absolutely not. The lowest one was 40. So this would be 0 out of 4, which of course is 0%, which is safely less than 20%. So we're all good there. Would it have been okay if one of them had been less than 5? Like say this other had come in as like 3 or 4 or something? No. Then we would have been in trouble because this would have been 1 out of 4. 1 out of 4 would be 25%, and we would fail this condition. So in this one, they all had to come in less than 5 because we only had 4 expected counts. All right, now we are ready to go ahead and do our computation. So we're going to do our test statistic. So for our test statistic, same formula as we used in the previous one. So we're taking the sum of the observed counts minus the expected counts squared over those expected counts. So we know that the expected counts are right here. Where are the observed counts? Well, that is our actual data. We haven't actually used that yet, so now is the time. This is our observed counts here. So let's go ahead and do this. We should have 4 computations to do. Once again, I'll sort of draw a dividing line just to make that a little clearer. Okay, so our first observed count is we observed 65 El Camino students pick action. We expected 50. So it's going to be 65 minus 50 squared over 50 plus we observed 69 students choose comedy versus 66. So 69 minus 66 squared over 66 plus we observed 27 choose drama against an expectation of 44. So 27 minus 44 squared over 44. Plus finally, we observed 39 choose other versus an expectation of 40. So 39 minus 40 squared over 40. Again, remember when you're doing this, the really crucial thing is that you are always dividing by the expected counts down there. All right, so let's go ahead and plug this stuff in and actually calculate it. So 65 minus 50, we'll square that and divide by 50. Looks like our first one should come in as 4.5 plus then 69 minus 66 squared and then divided by 66. Looks like we should get plus 0.14 and then 27 minus 44 squared divided by 44. We can see that that comes in as about 6.6. And then finally, 39 minus 40 squared and then divided by 40. We should get plus 0.03. Summing all that up, 4.5 plus 0.14 plus 6.6 plus 0.03. Looks like we should get about 11.27 as our chi-squared statistic overall. Again, why do we take the time to write out all of these sort of separately? Well, this tells us that if there is evidence, where that evidence is coming from, right? We can see, like in this case, that the largest one came from this 6.6, which was our third calculation right here. That's where we observed 27 choosing drama against an expectation of 44. That was, according to our calculation, the biggest difference between what we observed and what we expected. So if we do find evidence that El Camino students have a different taste in movies than the rest of the U.S. population, part of our sort of follow-up analysis could be to specifically analyze if El Camino students have a less interest or the general population has more interest in dramas overall, because we saw this big difference between this 27 in our observed versus an expectation of 44. All right, let's go ahead and get our p-value. So for the p-value, we need to go on to table D. So to do that, we need to have our degrees of freedom. How do we do that here? Well, similar to independence and homogeneity, we look at the number of choices we have for the variable minus 1. So in this case, we had 4 categories or 4 choices. So minus 1, we get a degrees of freedom. 4 minus 1 equals 3. So we have chi-squared being 11.27 and degrees of freedom 3. So let's go ahead. We'll do that on table D. So we have 3 degrees of freedom right here, and we have 11.27. So if we follow that, we should end up right there. So we'd be right here with our our 11.27. So where does that put us in terms of our p-value? Well, it puts us between the 0.02 and the 0.01. Remember, the p-values get smaller as we go this way. So we'll write 0.01 first, then our p-value, then 0.02. I'm sorry, this is a little mistake back here. This should not be a t. That's a chi-squared. Equals 2.001, because of course that's why we're using table D here, and this is chi-squared equals 11.27. So like we said, it's between 0.01 and 0.02. So let's go ahead and record that. So we just found that our p-value is somewhere sandwiched between 0.01 and 0.02. So it's bigger than 1%, but smaller than 2%. All right, let's go ahead and finish this on a next page here. So for step 5, we're ready to make our conclusion. We're going to take that p-value and compare it against the alpha that was set in the problem, which is 0.05. Remember, our p-value here is sandwiched between 1% and 2%. So how does that compare to 5%? Certainly, that means it is smaller. Whenever the p-value is smaller than alpha, that means that we have rejected the null and we've successfully found evidence for our claim. So we'd say significant evidence that. Now we have a choice here. How do we want to phrase the claim? Well, we could look at our alternate and say at least one of these proportions is different, or we could look at the claim in the actual text that El Camino students have a different movie preference than the rest of the U.S. population. Either way is appropriate here. So significant evidence that El Camino students have a different preference in movies compared to the U.S. population. So we are convinced that El Camino students' tastes in movies is different than the general U.S. population. And if we wanted to do further analysis, we'd probably start by analyzing are El Camino students less likely to like drama films compared to the rest of the U.S. population, because that's where we found the biggest significant contributor to our chi-squared test statistic. All right, let's do a couple little follow-up pieces to this. So in part B, we wanted to talk about what happens with a type 1 error. Remember, type 1 errors are false positives. So this means that this is where we reject HO, but HO is true. So to write out this error, we have to write two components. We have to say, what does it mean to reject HO, and what does it mean for HO to be true? Well, rejecting HO, we just phrased that up here, so let's make use of that. Rejecting HO means we believe there is significant evidence that ALCO students have a different preference in movies compared to the U.S. population. But in reality, what does it mean for HO to be true? Well, if we go back, HO being true was that all the values are equal to what they were for the U.S. So we would say, but in reality, their preferences are actually the same. So in other words, as usual, a type 1 is a false positive. We think something is going on, but it's really not. So we think that there is a difference between El Camino students and the general U.S. population in terms of movie preferences, but in reality, they're actually the same, a false positive. Finally, for part C, we wanted to talk about the sampling technique used. So remember, for sampling technique, we really have 5 choices. We have SRS, systematic, stratified, cluster, and convenience. Now, we know that since we're performing statistical procedures, statistical inference, it's not going to be convenience because that's not a valid way of sampling. We also know that it used the word random in there, meaning that we weren't using a mathematical system for randomness. It actually was done randomly, so we know it's not systematic. So the question is between SRS, stratified, and cluster. So let's go back and take a quick look at how we actually got this data. Notice that we selected 8 classes, but ended up with 200 students. So the classes were not the individuals. The individuals were each individual student. But we got the 200 students by picking 8 classes and talking to every student in those classes. So remember, whenever the number of selections doesn't match up with the sample size, so selected 8 classes, ended up with 200 students, that means this is a cluster sample, because each time we picked a class, we took every student in that class in that cluster. So this right here would be a cluster sample. And the clusters, right, the clusters were the classes. So we picked 8 classes, and then each of those classes had maybe 20, 30 some students in it, so we ended up with our 200 students. All right, let's get to the last question, question 3 here. So for question 3, we're going to suppose that a school district is studying if different reading programs for their 5th grade students impacts their average reading speed by the end of the year. So to study this, the school district, which you can assume has lots of 5th grade students, randomly selects some students to be placed into one of 3 programs, and they call these programs Program 1, Program 2, and Program 3. These students are then tested at the end of the year, and their reading speed is measured in words per minute. So they get the following data. So here's the students who were in Program 1. There was a student in Program 1 who had a reading speed of 113 words per minute at the end of the program, somebody 136, somebody 152, etc. In Program 2, we can see that they had 100 and 105 all the way up to 146. And in Program 3, somebody was as low as 92, somebody was at 127, somebody was all the way up at 159. So we're going to carry out a hypothesis test at alpha equals 0.05 to test the claim that there is a difference in the average reading speeds for the students in these 3 different programs. Okay, and then part B, we'll do a confidence interval. So again, we're doing part A here. So this is a hypothesis test, which means we need to identify which type of hypothesis test. Well, the first key thing in this here is that there's this mention of average. As soon as you see average, you know we're talking about quantitative data. So we might be doing a 1 sample mean, a 2 sample mean, a matched pairs, or an ANOVA. Well, how many sets of data do we have here? Well, we've got 1, 2, 3 programs. So that means it's not a 1 sample, it's not a 2 sample, and it's not matched pairs. It has to be ANOVA because we have 3 or more samples of quantitative data. So this is going to be an ANOVA hypothesis test. Remember, that's 3 or more samples of quantitative data. So we know that this is going to be an ANOVA hypothesis test. That also means that we probably know we're going to need to calculate things like the average and standard deviation, and we're going to use our calculator to take care of the test. So now is not a bad idea to go ahead and pop this data into L1, L2, and L3. So I'm just going to go ahead and do that real quick. Probably a good idea to go ahead and follow along as well. So in L1, we'll put all the Program 1 students, so 113, 122, 128, 135, 136, 137, 138, 146, 148, and 152. Then in L2, we've got 100, 105, 112, 118, 119, 124, 125, 126, 128, 137, 139, and 146. And then finally in L3, we will put all the Program 3 students, 92, 106, 117, 118, 126, 127, 128, 134, 137, 145, and 159. All right, probably not a bad idea also to just go ahead and get their mean and standard deviation for each group. We will need that. We'll need at least the standard deviations later on when we get to the conditions of the ANOVA test. And also, just looking ahead, we do have a confidence interval to build, at least for Program 3, so we're certainly going to need the mean and standard deviation for Program 3. So let's go ahead and do one variable stats on all of these. So we'll do stat, calc, 1 variable stats. We'll do L1 first, and I'll just record that stuff here. The average for L1 looks like their average reading speed was 135.5 words per minute, and their standard deviation after rounding to, we'll just round to 1 decimal place, looks like it come out as 12.0. Remember, you do want to use sample standard deviation here. For the second one, we'll do stat, calc, 1 var stats. Make sure to put in L2 now, though. And looks like their average was 123.3, and their standard deviation was 13.6. So a slightly lower average reading speed and a slightly higher amount of deviation, which should make sense. I mean, they're ranging all the way from 100 all the way up to 146. These guys were only 113 to 152, so a little more deviation in that group. And then for L3, we do stat calc, put in L3 now, and it looks like the average there should be approximately 126.3, and the standard deviation there should be about 18.3. Not a surprise that they had the most deviation, considering they had the lowest, 92, and also the highest, 159. Okay, so let's go ahead then and actually start this Anova hypothesis test now that we have that preliminary stuff out of the way. So first we need to start with our hypotheses. So HO and HA. Remember that the baseline assumption, the null hypothesis for an Anova test, is always that the average for each population, or in this case each program, is going to be the same. So we're going to say mu1 equals mu2 equals mu3. If we had a fourth program, we'd put equals mu4. But for now, we just have 3, so mu1 equals mu2 equals mu3. What's the alternate? Well, we're saying at least one program's average is different than the others. Now, we always go ahead and write out that alternate in words, and also keep in mind that this can mean a lot of different things. This could mean that program 1 is different than program 2, which is also different than program 3. Or it could mean that maybe program 1 and 2 have the same average, but program 3 is different. Or maybe programs 1 and 3 are the same, and program 2 is different. This is just saying there's at least one program's average, maybe more, that is different. Or maybe they're all different, but the alternate takes into account all those possibilities. That's what makes this a global hypothesis test. All right, let's move to the conditions. So remember, for Anova tests, the actual calculation is going to be all done by the calculator, but the conditions is where you have a lot of sort of the work to do. So first, we need all the samples to be random and representative. And of course, they randomly select some students to be placed into one of 3 programs. So that is definitely stated. So we're all good there. Then we need to make sure that all samples less than 5% of the population size. But if we see here, we can see that they mention that you can assume that there are lots of 5th grade students. So we can just say that right there. Lots of students to choose from. So we're all good. For condition 3, all right, this is where we have to confirm that the data sets are either each greater than or equal to 30, or we have to do stem and leaf plots. If we go back and look here, we can see that none of these had more than 30 data points, so we're going to be doing stem and leaf plots for each of these. So we need to make sure data approximately normal. So I think I'll go ahead and we can, it'll be a little bit easier if we just swing those up here. So let's do program 1. So if we look at program 1, looks like we'll have to have stems of like 11 all the way up to 15. So I guess we can do like 11, 12, 13, 14, 15. And it looks like we should have 1, 1, 3, 1, 2, 2, 2, 8, 35, 36, 37, 38, 46, 48, and 52. And does that look approximately normal? Yep, we're all good with program 1 here. So I'll just make a note over here that this is program 1. So we're all good with that guy. Let's do program 2 right here. For program 2, looks like we have to have stems of like 10 through 14. So 10, 12, 10, 11, 12, 13, and 14. So it looks like we'd have 100, 105, 112, 118, 119, 124, 125, 126, 128, 137, 139, and 146. Okay, is this perfect? No, I mean, it's a little sort of lumpier over here than it is here. But again, there's no strong skew, no outliers. Again, outliers are the real thing we want to avoid, so we're all good there. And then for P3, we have 9, 10, 11, 12, 13, 14, and 15. So notice I had to have a stem of 9 here to deal with that 92. So there's 92, 106, 117, 118, 126, 127, 128, 134, 137, 145, 159. Notice even just visually, you can see that this guy is more spread out, right? And we had more stems, and there's sort of the tails are longer, but it still looks pretty normal. It's symmetric, no strong skew, no outliers. We are all good. Good idea to include a key, and the nice thing is that the key in this case, we can actually do it for all three. So we can just make a little note like 11/3 actually equals 113 words per minute. So nice to include a key there because it applies to all of them. All right, so condition 3 is satisfied. Each of the samples seems to be approximately normal. Remember, the Anova test is special, though, because it does have a fourth condition. So that fourth condition is about the sample standard deviations. We have to make sure that the max sample standard deviation is less than 2 times the minimum sample standard deviation. Remember that what this is doing is that this is a practical way of checking that the population standard deviations are equivalent for our 3 programs. We can't check that because we don't have access to the population standard deviations because we don't have the full populations. We only have samples. But we can check this by looking at the sample standard deviations. So we want to make sure that the maximum sample standard deviation is less than 2 times the minimum. So what was the maximum one? Well, looking back up here, it was at 18.3. So we just want to check, is 18.3 really less than 2 times the minimum? Which one had the minimum? Well, it was program 1, that 12.0. So let's put that 12.0 there. And if we check that on our calculator, 2 times 12.0, we should get 24 there. Is that a true statement? 18.3 less than 24? Yep, we are all good. So condition 4 is also satisfied. Remember, out of all the hypothesis tests you guys have learned, only the Anova test has 4 conditions. Everything else just has 3. All right, let's go ahead, give ourselves a fresh page, and finish this up. So now we're ready to go to steps 3 and 4, which are the test statistic and p-value. Since we use the calculator to handle the Anova calculations, this step we can just put these two together. We put steps 3 and 4 together. Remember that to do this, we're going to go to Anova, which is under the Stat and then Tests menu. So we're going, just to write that out, we're going Stat and then Tests, and then we're going to find Anova, and then we do Anova. It gives you a parenthesis already. Put in L1, comma, L2, comma, L3. Close up the parentheses. So let's do that. Stat, tests, go to Anova. L1, comma, L2, comma, L3. Close up the parentheses and hit Enter. Remember, we're going to record 2 things. We want to record the F statistic. This is the test statistic. In this case, it looks like it comes out as about 1.95. That is the test statistic. And we also want to record the p-value, which looks like it comes out in this case as about 0.16. So we've got our 0.160, I suppose, if we keep 3 decimals, which we usually do for this. So there we go. There's our F statistic and our p-value. Now again, because we're using the calculator to do this, the F statistic doesn't really, we don't need it, but it's good to be consistent, write it down anyway, so we include it there. So we've got our F statistic and our p-value. Now we're ready for step 5, the conclusion. So let's go ahead and do that. The p-value against the alpha of 0.05 that was set in the problem. This p-value, this is about 16% versus 5%. Clearly, the p-value is larger than alpha. That means we're going to make the statistical conclusion of fail to reject HO. And that means we have no significant evidence for our claim. So no significant evidence that, what was our claim? Well, we can look back at the language of the problem to claim that there's a difference in the average reading speeds for students in these 3 programs. Or we can say at least one of the program's averages is different than the others. Either way you want to phrase it. So no significant evidence that the average reading speed is different after these 3 programs. So at least according to our analysis, we're not seeing any change between these three different programs in terms of average reading speed. Does that mean that the programs are good or bad? No, it just means that they're not different. They could all be good, they could all be bad, they could all be sort of middle level. We're just saying we're not really seeing any evidence that their average reading speed is different after these three different programs. Or between these three different programs, maybe a better way of phrasing it. All right, so there is an Anova test. Let's go ahead and wrap this up with one quick confidence interval. We also wanted to build a 95% confidence interval for the average reading speed for students in program 3. So what type of confidence interval are we going to be building? Well, we're building a 95% confidence interval for the average. So that either means one sample mean, two sample mean, or matched pairs. Clearly not going to be matched pairs. And since we are only looking at students in program 3, this is going to be a one sample mean confidence interval. So we can do that right here for part B. It's going to be a one sample mean confidence interval just applied to the program 3 data. So for the conditions, well, what are the conditions for a one sample mean confidence interval? The first two are always the same, random and representative, sample size less than 5% of the population size. We've already checked those. The third condition would be that the data has more than 30 data points or is approximately normal. We've already checked that as well. So in this case, we can just say already checked. So we're all good there. For 2, we can go to the construction. What is the formula for a one sample mean confidence interval? Well, it's that x bar plus or minus t star s over root n. So what do we need to know? We need to know x bar, s, n, and t star. So remember, this x bar, s, and n are all going to apply to the program 3 data. So let's go find that. We can go back and see that in program 3, the average was 126.3. So we can record that. 126.3. The standard deviation was 18.3. So 18.3. And the sample size, well, we can just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we had 11 students in program 3 that were selected. So there we go. What about the T star? Well, we'll have to look that up. This is going to be on table C, 95%, and we'll need to have the degrees of freedom. Remember, for T star, degrees of freedom is 1 less than the sample size. So in this case, degrees of freedom is going to be 10. Put those two together. Let's go ahead and do that. I guess we can do it in red. 95%, 10 degrees of freedom. So 95%, 10 degrees of freedom. Put those together. Looks like we should get 2.228. So our T star in this case, 2.228. Let's go ahead and plug all that stuff in. 126.3 plus or minus 2.228. 18.3 divided by square root of 11. We'll go ahead and calculate that margin of error first. So 2.228 times 18.3 and then divided by square root of 11. And it looks like we should get 126.3 plus or minus 12.3. We'll go ahead and build our interval. 126.3 minus 12.3. Looks like we should get 114 as the low end, and 126.3 plus 12.3 looks like we should get 138.6 as the high end. So what does that actually mean then? Well, we'd say we're 95% confident that the average reading speed in program 3 is between 114 and 138.6 words per minute. Does this mean that 95% of the students in program 3 end up in here? Not at all, right? Because again, remember, confidence intervals for means don't apply to individuals. But this is saying we're 95% confident that the average reading speed for all students, so putting all the students who finish program 3 together, should land in this interval. 95% confident that it'll land in that interval. So there we go. There's a little bit of sort of a review of a confidence interval following up an Anova procedure. That wraps up practice 11.